Hello everybody and welcome back to another visual pattern challenge. Here's our pattern today. Here's step 1, here's step 2, here's step 3, and your challenge is to predict the number of cylinders in step 4. If you can do that, can you predict the number in step 43? And can you write an equation that could be used to predict the number of cylinders in any step at all? I think this one is pretty difficult, but if you'd like to accept this challenge, pause the video, see how far you can get. Okay, so at first glance, this pattern doesn't seem to be growing super fast. So maybe just linear, although when I look at what's being added, it looks like these columns are being added. And so there's an additional column and the column gets longer. So that would say it's growing in two directions. And I would think it would be quadratic. Well, let's just use our visual intuition to get a sense of step 4. So we start with one cylinder, and then there's the one cylinder. It looks like we add a column of 3. And then there's our one cylinder in our column of 3. Then we added a column of 4. Okay, so we're adding a column of 3, adding a column of 4. So I would expect in the next step you'd add a column of 5. And there'd still be that column of 4, that column of 3, and the one from before. So what is that? 9, 12, 13. So my prediction for step 4 is 13 cylinders. Let's take a minute to analyze these numbers so we can really see, is this quadratic or not? So I'm going to make a chart with the step number and the number of cylinders. So in step 1, we've got 1. In 2, that's 4. In 3, that's 8. And we're saying 13 for step 4. And to analyze, of course, we take the difference between each step. So 4 minus 1 is 3, 8 minus 4 is 4, and 13 minus 8 is 5. So we didn't get a constant in the differences, which means it's not linear. And the next thing we can do is take the difference of these differences. So 4 minus 3 is 1, and 5 minus 4 is 1. So we did get a constant there. If you get a constant in the second order differences, in the difference of the differences, that means it's a quadratic. So an x squared is involved in some way. And actually, we know a little bit more than that because this number, this constant you end up with, if you divide it by 2, that's the coefficient of your leading term in your equation. So 1/2 x squared figures into this equation somehow. It's not the equation though, right? Because 1/2 of 1 squared is not 1. 1/2 of 2 squared is not 4. So something else is going on here. And previously, we've used some different strategies. Sometimes we've tried to block out the x squared part when we get a quadratic just visually and see what's left over and see if you can see any obvious patterns. Sometimes we made a list of numbers where we've sort of broken the total apart into the squared part and what's left over. For this particular pattern, I find those methods difficult. I don't see anything that leaps out at me when I try to block off a 1/2 x squared. I mean, think about it. In step 3, you'd be blocking off, 4.5 cylinders and seeing what's left over. It's not very useful, at least in my opinion. And I don't think analyzing the numbers helps a ton either. So I wanted to take this opportunity then, and maybe you've sorted this out. Maybe you figured this out on your own. You'd use some trial and error, which is probably the method I'd go to, is just some trial and error. But I wanted to show you another method, and you might think it's kind of like cheating, although I think of it more like knowing how to use all of the tools at your disposal. This is something you can try when you're absolutely stuck to figure out what an equation for a particular pattern is. And I'm going to use this tool called GeoGebra. So maybe you've used this before. This is kind of a fancy graphing calculator. And what we're going to do is we're just going to plot the points. So this chart, 1, 1, 2, 4, 3, 8, 4, 13, those are going to be our X and Y coordinates. And we're going to see what this looks like. So to plot a point, you just put parentheses and 1, 1. Did a period instead of a comma. 1, 1, there it goes. So there's our first point. And then the second point is 2, 4. And then we had 3, oops, parentheses, 3, 8. And then we had 4, 13. Okay, so I'm going to shrink this down a little bit so we can see all of our points there. So there they are. And that does look like one arm of a parabola. So this does fit with the idea that the leading coefficient would be 1/2 x squared. So that's nice to get that sort of visual representation. GeoGebra, and the reason I chose GeoGebra for this is that it has some really great tools. And one of them is that it will fit a polynomial to a set of data. So I think this is fit poly. Yeah, fit poly. And once you get the first few letters typed in, you can look it up. So it needs a list of points and a degree. Okay, so fit poly, and then A, B, C, D, and it looks like it's automatically going to degree too, but we'll put that in there as well. So I typed in fit poly, then A, B, C, D, and a degree. And there it is, right here. We have 0.5x squared plus 1.5x minus 1. Another way to write that would be 1/2 x squared plus 3/2 x minus 1. Would you have gotten that equation without using this tool, or maybe you did? If you did, I'd love to know how. So please tell me. You could have written this also as x squared plus 3x over 2, and then all of that minus 1. So that would be a way to do it. So we've got an equation. Actually, let's go ahead and jot that in here. So 1/2 x, 1/2 x squared plus 3/2 x minus 1 was what we came up with for our equation. How about step 43? I mean, plugging 43 in there is kind of a pain too. We certainly could do that, especially if we have a calculator. Luckily, we have a great calculator right here, and we can actually find the intersection of two items, I'm pretty sure. Yeah, intersect, and then it's just object and object. Okay, so intersect and parentheses. So one object is this function f, and the other object, would have to be missing a step here. We don't have anything to intersect with this, so I'm going to just make another line, x equals 43, because we want to know where x equals 43. So let me shrink this way down again. So there's x equals 43, and way up here somewhere, it's going to intersect with this function. So right there. Oh, and I don't even have to do the intersect. It did it for me. Wow. So if I typed in that command intersect f and eq1, it would have given me this, but I just had to look on the graph, and there's the point. So at 43, the y value is 988. What that means is when you plug in 43 into this equation, your answer is 988. So that is how to use GeoGebra when you come across a pattern that stumps you, where you're feeling really, really stuck and frustrated. So try out this fit poly thing. Graph the points, try out the fit poly, see if it works for you. It's a great tool. It's just geogebra.org. It's all free. So that is a little bit of work with this strange pattern and using a new tool to try to find an equation. How did that go for you? Were you stuck on this, or did you come up with this equation without using such a fancy tool? If you did, I'd love to hear about it. Thanks, everybody.